Okay. Well, thank you so much for the invitation. It's a shame I cannot be there with you in Cordoba, but I hope I can see you there soon. So today I will present low surface brightness galaxies in IllustrisTNG. It's part of my PhD thesis. I've been working with Bernardo Cervantes and Vicente Rodriguez here in Mexico, and in collaborations with many members of the Illustris collaboration. So I will start talking about, well, Gaspar already said a lot of things about low surface brightness galaxies, or LSBGs. Many observational works have allowed us to study the properties of these galaxies, but unfortunately these studies are limited to the local universe. Why? Because the diffuse nature of these galaxies do not let us look very, very far in redshift. So these observational studies are very limited to the local universe, so we cannot see clear evidence of what happened with these galaxies in the past. We are not very sure, as Gaspar said. We don't know what happened with these galaxies, why, how these galaxies form, and the formation mechanism cannot be completely understood. So have been these galaxies always be LSBGs, or which processes make them to evolve as LSBGs? Now, with the aim of cosmological simulations, we can observe how these galaxies were in the past. We can see many mechanisms, as Gaspar already presented in the previous talk. Here are many examples of works employing cosmological simulations to study the evolution of these objects, but in particular, I will talk about IllustrisTNG. So what we do, we use TNG to make an extensive study of the main properties of LSBGs at look at redshift 0, which allows us to select a population, a local population of LSBGs comparable, similar to observations, and then taking these galaxies at redshift 0, we look back in time how these galaxies evolve. So we first try to study the morphology, the star formation, the angular momentum, and the spin parameter of these galaxies. We build a synthetic sample comparable with observation, and we try to study some important mechanisms related with their evolution, such as mergers, star formation activity, accretion, etc. And we try to propose a feasible scenario to the formation of LSBGs. So this work is mainly centered in galaxies with stellar masses larger than 10 to the 9 solar masses, and we attempt to study the evolution of, let's say, intermediate mass LSBGs. So we do not reach as high stellar mass, such as 10 to the 12, for example, or something, because this falls in the regime of giant low surface brightness galaxies that Gaspar already said. So we focus on intermediate stellar mass galaxies, and we compute the surface brightness using this procedure. We orientate the galaxies as phase on, and then we calculate the effective radius that contains the half of the total luminosity. We calculate the apparent magnitude, and then we obtain the surface brightness according to this equation. And we classified these LSBGs as those which with this threshold in the R band. We employ, in this case, the R band because this band traces the intrinsic population of stellar content in these galaxies. For example, other bands like the B band employed by Freeman is more focused on the current star formation episodes and stuff like that. So if we want to trace the intrinsic stellar populations in these galaxies, we can employ this band of in the photometry. So this is the full sample of our galaxies, about 36,000 galaxies. And here we can observe two synthetic images of galaxies in our sample. These galaxies are similar in mass. They are about 10 to the 10.5 solar masses. And we can observe that LSBGs are more extended and diffuse than their high surface brightness, or HSBGs, counterparts. So here we have a circle that encloses the effective radius, and we see that the galaxies that are extended correspond to LSBGs. So many of these galaxies are presented in many morphologies, but in particular, LSBG population is dominated by galaxies with this value kappa is a fraction of the kinetic energy related with rotation divided by the total kinetic energy of the motion of the stars. And this is strongly related with the morphology of the galaxies. So we can observe that, well, spiral galaxies have higher values of kappa. So we can see that most of the population of LSBGs is strongly dominated by late tight objects such as spiral galaxies with small bulges and probably not too strong bars. So the global statistics that we found first in our sample is that LSBGs are found to be fainter, less massive and extended, and as we expected, because as we see, many observational studies have shown that these are some of the main properties of these galaxies, but we found no significant difference found in their specific star formation rates when we compare them with HSBGs. So this can be an indicative that, okay, these galaxies maybe are not as quiescent as we first we can think, but this could mean that the strong episodes of star formations are spread over larger time scales. So these galaxies are constantly forming stars, but not as strong episodes as other galaxies. So these galaxies, one way to see this phenomena is to analyze the gas content in these galaxies, and we can observe that at fixed stellar mass, LSBGs have systematically higher amounts of gas. We measured the H1, the H2, and the total neutral gas content, and we observed that this is a constant in the galaxies of our sample. But yeah, well, when we study the specific star formation rate, the color, and the median stellar age, we found that LSBGs are in general blue, as we can see in this plot, especially in the stellar masses we are focused on, and we see that galaxies have, well, this plot is not very clear for us, because we see, like, for example, there is no significant difference here, but then when the stellar mass rises, we see many differences in the specific star formation rates. But when we observe the color and the median stellar age, we found that galaxies have, in principle, slightly younger stellar populations, and they are slightly blue. So the main question is, where these episodes of star formation are occurring. We attempt to study the places where the star formation episodes are taken into part, and we found that the star formation is taking part in the outer region of these galaxies. Why? Because much of these galaxies, at least at high masses, the contribution of accreted stellar mass is very high. So the contribution and the accreted material turns on the stellar formation episodes, and that's why we can explain this behavior in this plot. So we want to study the angular momentum of these galaxies, and we have here the fold diagram that is basically the specific the specific angular momentum against the stellar mass. We compute here the retention fraction, defined as the specific angular momentum divided by the specific angular momentum of the dark matter component, and we have here the spin parameter, and the spin parameter measured within the 10% of the virial radius of the halo in which these galaxies reside. So we observed at fixed stellar mass that, as we already see in the previous talk, that LSBGs present systematically higher values of their specific angular momentum and the spin parameter. So this behavior is consistent not only with observational studies, but also with some yes, thank you. Some theoretical works, and we see that the retention fraction are well, the retention fraction of LSBGs is higher, not because of their nature of being LSBs, but is mainly related with the morphology of these galaxies. So we observe also that LSBGs are formed within halos of very similar dark matter mass, but when we look to the baryonic content, we see that LSBGs have higher baryonic fractions than HSBGs. So given that LSBGs are formed within halos with similar mass, the excess in baryonic budget must consist of gas. And finally, we want to look back in time, which are the main properties that favors the evolution of these galaxies. So we can observe that, well, the key parameter that we want to study is the spin parameter. So we can observe that at high redshift, these galaxies, well, this in this plot is not very clear, but in these two mass regimes, we can observe that the spin parameter is very similar between LSBs and HSBs, and then the evolutionary tracks diverge one from the other, and we observe like the first parameter that changes is the spin parameter, and then the evolution of the spin parameter, the changes in the spin parameter affects the evolution of the angular momentum and also the extension or the size of these galaxies. So this is like a cause consequence of derived from the evolution of the spin parameter. So this is maybe a good explanation of why these galaxies present high angular momentum and extended areas. So to finish my talk, I made a summary. So we find that LSBs are fainter, less massive, and gas-rich, and more extended than HSBs. At fixed stellar mass, these LSBs exhibit higher spin parameter and angular momentum retention fraction, and the combination of both results in the higher stellar angular momentum observed. So my main conclusion of this work is that LSBGs tend to be systems with high angular momentum and cold gas as a result of higher spin parameter of their host Taylor. But at least in this mass regime, from 10 to the 9 to 10 to the 12 stellar mass, secular evolution rather than accretion and merger seems to be the most feasible scenario of LSBs formations. We want to study what are the key parameters in the merger that raise the spin parameter of these galaxies, but this is part of a work in progress. But our main conclusions here is that in principle we can argue that the spin parameter rather than other properties are to be the most feasible scenario of LSBGs formation. And as Gaspar already said, the mergers take more relevance in the regime of the so-called giant LSBGs. So that's everything I have to show for now. So if you have any question, please do not hesitate to tell me. Hello?
Oh, yeah.
Hello, can you hear me?
Thank you. Thank you. So questions, David?
Very nice work, Luis Enrique. Did you check what about the environment, if LSB galaxies are in a particular environment with respect to high surface brightness galaxies?
Yes, I am. It's a work in progress. Actually, I have been working with this in the results I present here is like the first half of my thesis, but we have make some tests on the environment of these galaxies. So well, these are very preliminary results. We have to go further in discussion with these results. But for example, we found that the environment is relevant, but in low scales, such as groups or something. Because for example, well, I have these density contours that allows us to check, for example, that the fraction of central, well, the environment has, with this environment, the local environment has some impact depending if you are a central galaxy, if you are a satellite galaxy, if you are a spiral galaxy, if you are an elliptical galaxy, the behavior is very different between these very different kind of objects. But we also checked the two-point correlation function of these galaxies, and we observe, like, for example, LSBGs are less clustered than HSBs. And it also depends on what kind of galaxy we are studying. If we are studying spirals, if we are studying ellipticals, if we're studying blue galaxies, red galaxies. So the main, the global picture, at least on a first approximation, is like these galaxies, well, elliptical galaxies are formed, well, LSBs, elliptical galaxies, are formed by mergers, by interactions, or distortions and stuff. But the spiral galaxies evolve like secularly. So it's a very good picture to see how the environment affects the evolution of these galaxies, and it depends also what kind of morphological type your galaxy have. These are very preliminary results, but this seems to be in good agreement with other studies.
We have a couple of questions, but be brief.
Yes, okay. If you have any question, you can leave it in the Discord platform, and I will be very happy to answer them.
I have a small question. Thank you for the talk. So, is there any peculiarity about the dark matter content or distribution in these LSBGs respect to standard spirals, or none at all? As fine.
No, I haven't made the experiment, but we expect that for example, the distribution of dark matter and the rotation curves not be very different from what we found in observations. I don't know if I understood well the question, but
Jose Benavides seems to have a question. Do you still have your question, or can we move to the next?
Thanks, Luis. Yes, my question is in the same way of the previous question about the environment of morphologies for this kind of LSBs, but you respond this. Thank you.
Okay.
Okay, so we can move on with the next speaker. Let's thank again, to Luis.